Okay, first this is on Maxima, Minima, and the mean value theorem. Before we go through that, though, I want you to look at chapter 4 in your book. Open up your books to page 259. Okay, on page 259, it starts section 4.1, and this whole chapter is on applications of derivatives. If you look and go all the way back to the beginning of the year when we talked about doing complete graphs, the phrase, if they said draw a complete graph, we talked about you must show all the x and y intercepts. You must show all the max and min points. And then we also said you must not have any hidden behavior. This is the chapter where you'll be able to tell if there's any hidden behavior in your viewing window on your calculator. Okay, and the only way you can do that is through the calculus. Okay, if you look at the chapter first before you start with the notes, 4.1 we're going to do max, mins, points of inflection, critical points. We'll talk about the mean value theorem. We'll go through that in a minute. That's a little bit of section 4.1. Section 4.2 is where we talk about the section 4.2 is where we talk about the predicting the hidden behavior, being able to do that by using calculus. If you look at section 4.3, we'll talk about polynomial functions and Newton's method and optimization. If you look at section 4.4 on rational functions and a little bit of economic applications, some of you will end up majoring in business, and you may end up in a business calc class. We've already talked in one of the sections in the last chapter about marginal cost. Marginal cost was the first derivative of cost, and marginal cost was actually the way you can predict or estimate the cost of producing one more of something. If you do the actual cost of producing one more and do the first derivative, marginal cost, they are very close. Marginal cost is an estimate of producing one more of something that you're making. Section 4.5 we'll get into radical and what they call transcendental functions. In section 4.6 we'll get into some applications on related rates of change. Section 4.7 actually gets into figuring anti-derivatives. We've spent all the time figuring derivatives, and now in section 4.7 that's going to get you ready for chapter 5 where we actually start going backwards. So section 4.7 is on anti-derivatives and initial value problems. Okay, and that's the end of the chapter. Okay, so let's go through now on max, min, and a little bit of the mean value theorem. Okay, first the author goes through on a graph the only places where a function f, or f of x, they're using f, can have an extreme value or, okay, number one, and that's in the interior part of the graph where f prime, or the first derivative, is 0. Another place where it can have extreme values are interior points where f prime or the derivative does not exist. Examples where the derivative, remember where the derivative did not exist, sharp corners, that's one point where the derivative does not exist. Where there was a tangent line, a vertical tangent line, where the derivative did not exist. Or where the points of infinity, where the derivative did not exist. Okay, and the third one, endpoints. Okay, at endpoints of the function. Of the function's domain. Now, an example on a graph, what this would look like. Okay, draw a coordinate axis. Okay, and let's say I give you this for a graph. And put an endpoint at both ends instead of the arrows. Okay, now go back and look. Extreme values occur where f prime is equal to 0. Okay, so f prime is equal to 0 where the slope of the tangent line is 0. Okay, where we have a horizontal tangent line. That would be an interior point where f prime is equal to 0. There would be another one down here where it'd have a horizontal tangent. There would be another one over here. There would be a horizontal tangent. So those three x values would be extreme values. The y values, or where those x values are, would be extreme values for the y values. Another point, at interior points where f prime does not exist, this would be an extreme value, where it's a sharp point. Another point where there's an extreme value is the endpoints. This would be an extreme value, and this would be an extreme value. Okay. Okay. Also, at this point, the author talks about absolute max and absolute minimum points. This one would be, this y value would be an absolute minimum. It is the lowest point on that graph. This point up here would be an absolute max. It is the highest y value on that graph. This would be a max, but it's not the absolute max. It's a max over a certain interval of the graph, so that is what they call a local max. This would be another local max. It's a maximum, but it's not the highest point on the graph. The highest point is the absolute max. This point, this y value would be a local min. It's not the absolute min because there's a y value less than. And this one would be another local min. It's a minimum over an interval of the graph, over a certain interval of x values. So there's local max and local mins and absolute max and absolute min. Absolute is the highest point. Absolute max and absolute min is the lowest point. Okay. Okay. Then the author also defines a critical point. Okay. By definition, in this section, a critical point is a point in the domain of a function f at which the first derivative f prime is equal to 0 or f prime does not exist. And you can go back up and look at the graph where the derivative equals 0. That's where it has the horizontal tangents, and the sharp corner, that's where it had no derivative existed. Okay, so we had 3 critical points. Okay. Then the author actually gets a little bit ahead of himself in this section and defines and talks about some things in section 4.2. So I'm going to go ahead and mention them here. If you look at page 273 in the next section, the author talks about concavity of a graph. And we talk about a graph being concave up or concave down. If you look at a graph, this is what concave up looks like. Concave up on a graph, if you just do a little graph, coordinate axis. If you have a graph that looks like this is considered concave up. Okay, and then if you have a graph, and it's just like you can guess what this one's going to be if it's concave down. Okay, if I have a graph that's concave down, it's going to look like this. Okay, so when they talk about the concavity of a graph, that's what they're talking about. Concave up, concave down. Same thing the author talks in this section, gets a little bit ahead of himself. On page 275 in the book, the author defines a point of inflection. Okay, a point of inflection. It is a point where the graph of a function has a tangent line and the concavity changes. Okay, and basically to find a point of inflection, you have to have 2 things. The second derivative, f double prime or y double prime, has to equal 0, and a change in concavity. So you have to set y double prime, find the second derivative, set it equal to 0, solve for x, and then you also have to make sure there is a change in concavity. And we'll do some more of that in the next section. Okay, this is what a point of inflection looks like. And it would be very similar if you graphed a cubic like y equals x cubed. But this one is just going to be a little bit different than that if we're not on the origin. Okay, and there would be a point of inflection right about here. Okay, and then there would be a tangent line right about here. It's not where y prime equals 0, it's where y double prime equals 0. Another example for a point of inflection, you might have one that looks like this. Notice it changes concavity, and the point of inflection would be about right here. Okay, and the tangent line would be about like that. Okay, this one it changes from concave down to concave up. This one it changes from concave up to concave down. Okay, so they are considered, these x values and y values, the ordered pairs would be points of inflection. Okay. Okay, then the author also talks about the only points where a function can take on extreme values. The only points where a function can take on extreme values are critical points, critical points and endpoints. Remember, the critical points were where the function f prime equals 0 and f prime does not exist. If you include the endpoints, then those are extreme values. So extreme values are both critical points and endpoints. Okay, then the author defined, the author goes through the first derivative theorem for local extreme values. This is called the first derivative theorem for local extreme values. First derivative theorem for local extreme values. Okay, and it says if a function f has a local max or local min value at an interior point if a function f has a local max or a local min value at an interior point C of its domain, and if f prime, the first derivative, exists at C. So that's telling you over an interval, okay, if there is a local max or a local min and the derivative exists, then what does that derivative equal? Then f prime of C, if it exists and it's a max or a min, you already know this one, the derivative equals 0. If it didn't exist, then it would be one of those sharp, like a sharp corner or vertical tangent, okay, or at infinity. Okay. The next thing the author goes through is, this is a French mathematician. It looks like Rolle's theorem, but I think it's probably pronounced Rolle's theorem. Says, suppose, Rolle's theorem says, suppose y equals f of x is continuous at every point of a closed interval AB Remember our symbol for closed intervals we used at the beginning of the year? Closed means it includes those endpoints A and B. Suppose y equals f of x is continuous at every point of a closed interval AB. That means if it's continuous, you can draw the graph without lifting your pencil. And differentiable at every point of its interior, and they're using the open interval AB, and that means it's differentiable at every point in between. Okay, that means you can find the derivative at every point in between if f of a, and remember f of x, f of a, that stands for a y value. If f of a equals f of b, and both those are equal to 0, think where that is on the graph. If your y value equals 0, then there is at least one number c, that's an x value, between a and b, if f of a equals f of b equals 0, then there's at least one number c between a and b at which f prime of c. Now, if you looked at a graph, what they're really saying graphically, if I give you a picture like this, let's say this was A and this was B, and my y value, okay, if both those y values are equal to 0, then there has to be one number c in between A and B where this derivative is equal to 0. Right? Whether it's like that on the graph, or if I did the same thing and graphed something like this. If this is A, this x value is B. If those two are y values equal 0, then there's got to be some c in between where the derivative, the slope of the tangent line, has to equal 0. Okay? So basically you're going to have a max or a min in between. Okay? And that's Rolle's theorem. Okay? Then there is a contrapositive of Rolle's theorem. You did a little bit of that in geometry. This is the contrapositive of Rolle's theorem. Okay, the contrapositive of Rolle's theorem. It says if f prime, the first derivative of x, does not equal 0 for all, and remember, a lot of times in upper level math you're going to see the upside down A stand for all, for every, for any, for all x's. Okay, now think about this. If the derivative does not equal 0 for all the x's, that means you're not going to have any max or min points, because you're not going to have any places where the slope of the tangent line is equal to 0. Okay, then f has no more than 1, 0, or root. That means your graph, picture-wise, your graph is only going to intersect the x-axis in one point. There's only 1, 0, or root Because if it came back down, you would have a max or a min point. Okay. Okay, so if f prime does not equal 0 for all x's, then f has no more than 1 0 or root. Okay, the next thing the author goes through in this section is what they call the mean value theorem. Okay? It's called the mean value. It doesn't mean mean as in angry. It's mean as in average. The mean value theorem. Okay, I'm going to go through this and then I'm going to show you what it means picture-wise. If y equals f of x is continuous, at every point of the closed interval, if y equals f of x is continuous, that means you can draw it without lifting your pencil, at every point of the closed interval AB, remember you want to use brackets, that means it includes the endpoints, and differentiable, that means you can find the derivative at every point of its interior AB. That means you're not going to have any sharp corners, you're not going to have any vertical tangents, you're not going to have any infinity. Okay. Then there is at least one number C between A and B at which the first derivative at that C equals the f of B minus f of A all over B minus A. And what that really is, that is your formula for slope. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's what you did in algebra. Okay. Now, what that means graphically, it means that somewhere between A and B, the curve has at least one tangent parallel to the secant line AB. Okay, and graphically it looks like this. If I had a graph, and let's say the curve of the graph was something like this, and let's say this, I'm going to make this A, this X value I'm going to make B, and if I figure the slope of this line, okay, between A and B, then there's got to be some point C between there where there is a tangent line that is parallel to that secant line. This red line would be the tangent line. Okay, and there's some point, some x value c, where it's got the same slope as that secant line that's the blue line. Okay. If you look on page 267, if you look at that example 5 on page 267, it says if a car takes 8 seconds to drive 352 feet, its average velocity for the 8-second interval is 352 divided by 8, or 44 feet per second, or that's equivalent to 30 miles per hour. At some point during the acceleration, that theorem says that the speedometer had to have read exactly 30. Okay? So look at that example on page 267. You can look at that again. Okay? Then there is a corollary. Okay? This is corollary 1. And it is actually called the first derivative test. The first derivative test for increasing. The first derivative test for increasing and decreasing. And that corollary says f, the function, f increases when the first derivative, f prime, is greater than 0. So the function is actually increasing when the slope is positive. And decreases, f decreases, when f prime is less than 0. When the slope is negative, your function decreases. Now let's look at a graph. I'll show you what I mean. If I have a graph, let's say the graph looks like this. Okay? And I want to know where is that function. That's the original function graph. Where is that graph increasing? It's everywhere it has a positive slope, a tangent line with a positive slope. So it'd be positive, 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 okay, and then positive, and as soon as I get a horizontal tangent, okay. So if I said this graph is increasing, okay, it increases from negative infinity to 0, where that x value is 0 is where, okay, it's down here. So it's from the x value would be negative infinity to 0 is where it increases, and then it also increases if I said, okay, let's let this be x value of 3. It also increases or has a positive slope from 3 to positive infinity. Now, when I'm talking positive infinity, I'm not talking positive infinity up. I'm talking about positive infinity going out here to the right. Same thing, I'm talking negative infinity going out to the left. So it's everywhere it has a positive slope. Notice I put the union symbol, okay, just every time you have to separate it into sections, you're going to put the union symbol. Okay, and that means this graph is decreasing everywhere it has a negative slope. Well, it would have a negative slope from, look at the tangent lines, it would have a negative slope from 0 to 3. Okay, and notice on those you use parentheses for sure on the infinities. Sometimes the author switches and uses a bracket on the 0 and the 3. And I'm thinking I'm going to use the parentheses, but you can check in the back of the book. Okay? Okay, now the next thing you should do is read that section. Read section 4.1. Finish up notebooks. Remember, don't hand a notebook in to a sub. Make sure you hand it in to me personally. Okay?